I want to take our idea of linear approximations and leverage it a lot. So we were using an approximation for square roots to give me a rough idea as to what that number really is by hand. But even if I could leave my stuff in irrationals, I can always solve any square root equation because I know the quadratic formula. There's an equally available formula for a cubic equation. In the 1500s, Girolamo Cardano and Niccolo Tartaglia, in competition with one another, came up with a formula for this, which sucks. I have never memorized this. I'm not going to. I don't think you should either. It's horrible. No. Look, I've got a square root inside a cube root twice. No, I'm not doing this. But it turns out it gets worse before it gets better. Actually, it gets worse before it gets worse. If I go to a degree 4 equation, there are 4 different solutions. Ready? I can't even read the damn thing, can you? The only way I could get it to fit on one sheet of paper was to print it at this size. You'll pardon my bluntness, this. Not just no, hell no. Here's where it gets worse. When I get to degree 5, there are no formulas. None. A guy by the name of Niels Heinrich Abel was able to show that any polynomial whose highest power of x is 5 is not solvable using roots, powers, addition, multiplication, subtraction, the normal operations like we like. You just can't do it. Well, my linear approximation method allows me to get close. I mean, that's how we did the square root of 17, the square root of 37. I can do those rather easily. I could do the cube root of 9, right? The same way. I could get a linear approximation for the cube root of 9. But let me think about what we're actually doing. When I want to find the cube root of 9, what I'm really asking you to find is the root of this equation. If I had Cardano's formula in my head, I could figure out what this was. I already told you I'm not memorizing that crap. Graph this. X to the cube goes like this. We shift it down 9 units. There's my root. That's the number I want to find. Let's call it R. What's a number close to 9 whose cube root you know? 8. because 8 is the cubed of 2. So I could say, let's start with 8 and do a linear approximation. Start with 2, right? Because that would be where we put our tangent line. Our tangent line would go at 2, which would be down here somewhere, right? What's f of 2? What's f of 2? -1. And what I would do is I would draw a tangent line. That was what my linear approximation said to do. Make a tangent line whose slope is determined here. Hey, wait a minute. That's going to cross the x-axis somewhere, isn't it? And that crossing of the x-axis is going to be close to our root. Oh. I haven't figured out what the slope is, but the slope of that tangent line would be the derivative at 2. So there's the equation for my tangent line. Matter of fact, I could write it in general. But it's the x-intercept. It's the x-intercept of this line that I'm interested in, because that's the number that's close to our answer. What do I know about any point that's on the x-axis? Y is 0. Wait a minute. I can take that expression and solve it for x. That's the x-intercept of my line. And I've gotten a value that's on the x-axis close to my root. If I repeat this process using this new x value as a, I'll get another point from another tangent line. So what we just did was we started with some point, found the tangent line on our graph, and got another point. What's going to happen if I do it again? I'll go up to the graph. I'll draw another tangent line. Hey, wait a minute. That tangent line is going to get even closer, isn't it? And again, and again, and again. With nothing but my tangent line, I can build a sequence that closes in on R for any equation. If we think of this as a sequence and my starting point instead of A is x1, then the next point I get is x2, and the next point I get is x3, we can rewrite this formula ever so slightly and say that xn plus 1 is xn minus f of xn over f prime of xn. I don't care what equation we are looking at. If you want to find the root of the equation, we can get there from here. Nicolina? The xn plus 1 is xn minus f of xn over f prime of xn. So you take the x value you start with, plug it into the function, plug it in the derivative, subtract, and you get a new x value. Because that's our f of value, right? That's going to be here. And then I need to calculate f prime to go here. Let's do this. F of x is x cubed minus 9. And I am going to start with 2. So I know, according to this formula right here, that x2 will be x1 minus f of x1 over f prime of x1. I need f prime of x. What's f prime of x? When I plug 2 into the original equation, we got 1. Sorry, we got negative 1. Helps if I write down the correct number. Plug in 2 to the derivative. Say again? 12. 3 times 2 squared. So the correct answer is 2 plus 1/12. Okay. But I don't know that that's exactly right. Matter of fact, I want to keep going. How many decimal places do you want this number to? Because there are infinitely many 3's after this one. How many more decimal places do you think I should get? We only go for 4 decimal places. So I want to keep doing this until the number I get is the same for the first 4 decimal places 2 times in a row. So we're going to do this again. x3 is x2 minus f of x2 over f prime of x2. Now, this is about to get messy in terms of the numbers we're doing with, right? So let's cheat. We graphed this equation. I want f of this number. Trace. Put in 2 plus 1 over 12. There's my y value. The y value is pretty close to 0. I'm not that far off already. But that's not 0. So that number goes here. Four two two four 537 over. Now I need f prime. I could plug in by hand the 2.083 into 3x squared. But the calculator, on above the trace button, it says calculate, can calculate for me option number 6. the value of the derivative at a point I give it. Go down to option number 6. Oh, what point do I want to plug in? I want to plug in 2.0833333333. There's my derivative. 13.020834. Calculate this. Give me a number. If I want to keep all the right decimals, it's 2.05088855, or I just round up to 9 on the last decimal there. Because I'm only keeping 5 at the moment. But does x2 match x1 to 4 decimal? Sorry, x3 match x2 to 4 decimal places? Then do it again. Trace. Put in this number. 2.05089. Notice the y value this time is negative. Calculate the derivative at 2.05089. 12.61845. Repeat the process. Minus a negative becomes plus 0.3736495 divided by 12.61845. I went back up a little. See what I'm going to do? I'm going to balance back and forth and bounce in and get closer each time. At some point, I'll be close enough that those numbers will be the same 4 decimal places in a row. But not yet, so do it again. Point 005. Oh, this number is really small for f of. And I need the derivative there. Second, calculate option 6 at 2.08050, 12.985442. Repeat the arithmetic. $2.08008. The only difference now is in the 4th decimal place, right? I've got 3 decimal places that match. So if I was going to 3 decimal places, I could stop right here. But I said 4 decimal places. That'll teach me to pick a number out of my ass. One more time. Trace. Put in x equals 2.08008. Oh, look at that. What's that number mean? Somebody say it a little louder. Yeah, but I need to actually write down this number, right? Aha, 10 to the negative fifth. That's what that E stands for. So I got to move the decimal place over. 4 zeros. Negative 0.00004962. Calculate the slope at 2.08008, and you get 12.980199. Now we do the arithmetic again. 2.08008 plus 0.00004692 divided by 12.980199. Hot damn. So the cube root of 9, according to my calculation, is 2.0801 if I round the 4 decimal places. But I can actually find out the cube root of 9. Not only was I right to 4 decimal places, I'm actually right to 6 decimal places. And all I used was a straight line over and over and over. There's a reason linear approximations are taught to you. It's not just, oh, I need a number. It's how close do you want to be? This is, again, our epsilon delta idea. You tell me how close I need to get. I'll get there. Your calculator didn't magically come up with a 1/3 power using some crazy algorithm. It uses a modified version of this algorithm to get there. Questions? We can use any function you want. It doesn't have to be just a polynomial. It could be anything. Now, I'm claiming there's a negative root. We should graph this sucker and see what it looks like. E to the x plus x squared minus 4 looks like that. There's some place where we cross the x-axis over there on the left side. There is a negative root. What is it? I have the foggiest idea. But it's pretty damn close to -2, isn't it? So if I plug in -2, I get 0.13. That's pretty close to 0. So that'll be my starting point. And now I can churn through this one formula until I get 2 numbers that match to 6 decimal places. Go for it. So if that's the case, the text. I see. The issue you've got is you've got a very small window.
Yeah.
So let's reset that for a standard option. Now, there's our X cubed. All right. Oh, you have the signs the other way now. Plus X squared on this floor. Well, I typed them in backwards. There we go. Yeah, we had the window set on. I didn't write that down, did I? One, two, three, four, five, five. Get the zoom option. Go back to option 6. That's our standard window. That's minus 10.
Okay, thanks.
You're welcome. That definitely does not agree with the first one to 6 decimal places. So we do it again. How many times does it take you to get two numbers that agree to 6 decimal places? It only takes 4 shots. By the time I hit X3, my derivative is still negative. That changes the subtraction to addition. One more try. I get an E minus 7 on that number. Those match out to 6 decimal places. That's all I needed. How accurate do you want to be? Your calculator automatically has a tolerance built in of 10 to the negative 12. It would be searching for 12 decimal places to be the same when it does this routine. Questions? Yes, ma'am. I worked it out until I got to a degree and I'd already done it in advance. You just keep going until you hit the right number of decimal places. In this case, it was 4. Yes, sir. I would just write out, so my root is negative 1.964635, accurate to 6 decimal places. There are 2 possible problems. They're not huge, but there are possible problems with this idea. It is possible we could pick a really crappy first guess because our formula reads xn plus 1 is xn minus f of xn over f prime of xn. If I have a really crappy first guess, it might be that f prime of xn is 0. I have a vertical tangent line, in which case I can't do this. I screwed up, and I'll need a different choice. Just pick a number slightly to the left or the right, and let's see what happens. The other possibility is we are creating a sequence. And a sequence, in this case, we're looking, what happens is we keep going in the sequence, we're looking at a limit. Oh, all of the possible problems I have with limits come back and rear their ugly heads at me. It could be that I have a limit that doesn't exist. That the sequence we create never settles down. It is also possible to decide that I don't just want to work with real numbers. when you do the quadratic formula, it's possible you get a square root with a negative, right? What were you taught to do with those? What is the square root of -1? I, plus or minus I. We get what's called an imaginary unit. Personally, I hate that name. I don't think they should be imaginary at all. They're as real as the negative numbers are. I originally, when proposed by several people, was called a lateral unit because we think of them as kind of sideways to the regular numbers. A short diversion. What's square root of 4? I have 2 and I have -2. And we can think of squaring these as folding the negative part of the axis onto the positive part of the axis. Right? You take the negative number over there, when you square it, you go to the positive side. Watch my arm again. Take the negative number over here and you square it. You go to the positive side. Why this way? What if I went this way? Wouldn't I get the same spot? Okay, trig question. What angle is this? This direction. What angle is that? Angles in standard position. What angle is that? 0. What angle is that? I'm going to kill you all. How dare you use degrees in this class? Radians, pi, right? 180 degrees, yes. I understand. No. Never use degrees. Degrees are evil. Okay, save them for the physics class where those dumb people do it. No, you convert. Do everything in radians. What's 2 times 180? Doesn't that put you right back here? If I double the angle, I end up over here. So a square root can be thought of taking that angle and cutting it in half. What's half of 0? That's why there's a root on this side. What's half of 360? That's why there's a root on this side. Now, what angle is that? What's half of that? It's sideways. What's another angle that'll put you over here where -4 is? Other than 180 degrees or pi radians, what's another angle that'll do it? What is a coterminal angle? 3 pi over 2 is down here. Want to go this way? That's up here. What's over here? Well, that's pi, but it's also a whole circle plus a pi, isn't it? Which would be 3 pi. And half of that is 3 pi over 2. Isn't that down here? We can actually think of complex numbers as having angles involved. So I want to take this equation and I want to find the roots. What's the cube root of -1? Okay, but technically that means this equation factors. I know algebra class was a long time ago, but I can factor an equation once I know a root. X cubed plus 1 should be equal to x minus -1 times something. Well, there's got to be a quadratic in there. And I don't know if you remember how to do this quadratic. But you could divide if you really wanted to. You could divide out using long division. I think it sucks. But there is a formula for the difference of two cubes in the algebra textbook. This is a quadratic equation. If I use the quadratic equation, I get complex roots. The roots of this part are 1/2 plus or minus root 3 over 2i. Okay, hang on a second. If I think of the complex numbers as living on this plane, then -1 is over here. 1/2 plus root 3 over 2i would be up there. And 1/2 minus root 3 over 2i would be down here. Here's the best part. Newton's method still works in the complex numbers too. So if I wanted to find a starting point, I could pick a point anywhere on here, not just as a real number, but as a complex number. And maybe I'll end up here. But maybe I'll end up here or here. But maybe, just maybe, I'll pick a point whose limit doesn't exist. It's a little bit backwards from what I wanted. Let's turn it 180 degrees so it looks right. There's -1. Every red point in this picture goes to that root using Newton's method. Every blue point in this picture goes to 1/2 plus root 3 over 2i. Every green point goes to 1/2 minus root 3 over 2i. But there are a bunch of points that are white. They form the edges between these three colors, and they never, ever land on one of our points. They never converge to a limit. This is called a Newton's fractal, or the Newton basin of attraction for Newton's method. Newton never saw this. He had no idea. The different colored sets were discovered by a gentleman by the name of Fatou, and the properties of the set that is the boundary were discovered by the name of Gaston Julia. And this is part of what my thesis research was on. But this program, this picture, was generated by computer. And this method that we are doing the same thing over and over and over and over and over and over, is really boring. I know at least 5 of you are in CS and computer science and cybersecurity. Let's write code. This is a program available for the graphing calculator. The PDF file is the actual text. The .8xp file can be loaded directly onto your graphing calculator. All you have to do is plug it in. That lovely little USB port on your calculator allows you to load stuff into the calculator. You can download this program, put it right in here, and then program. And by the way, our equation is in there, right? I want to start with -2. Took us 4 steps to get done, to get numbers that matched. I'd love to tell you this is a worthwhile endeavor to do by hand over and over and over and over again. It sucks. Write code. What are we doing Wednesday? Wednesday is question and answer day because the homework is due Thursday and the exam is Friday. I just got a Penji announcement for a review session. I'll see you all later. Have a wonderful rest of your day.